You're listening to the Knowledge Archives podcast. Welcome to the Knowledge Archives podcast. We're a group of students on a mission to learn from as many different disciplines of knowledge as possible. I'm your host, Madhav Malhotra, and today I'm glad to be joined by Dr. Martin Tajmar, the director of the Institute for Aerospace Engineering at the Dresden University of Technology in Germany. He has over a decade of experience studying and developing advanced space propulsion systems like ion thrusters, so I'm very excited to learn more about his research in this futuristic discipline. I really appreciate you taking the time to join me today. I think it'll be a very interesting discussion to talk about the advanced areas of propulsion that you've been working in. But to start off, I'd love to just quickly ask you to introduce yourself and provide a little bit of context as to your background and past research interests.
Okay, all right. So my name is Martin Tajmar. I'm a professor and director of the Institute of Aerospace Engineering at the Technical University of Dresden, Germany. So that's one of the leading schools in Germany. And well, yeah, I've done propulsion kind of all my life. When I was very young, I watched Star Trek, right, on television. And I said, well, I would like to build something like that. And the most important piece was, of course, the warp drive. so everything else is doable or not maybe essential. But if you want to build a really cool starship, then you have to work on propulsion. So I studied physics, so I'm a physicist by education, but always with a strong focus on how to apply this on space. And so I was really very lucky working at various organizations. I've been at NASA JPL as a student. I worked for the European Space Agency. I worked for the largest research lab in Austria. And then I became professor at university here in Dresden. We're doing basically everything that deals with space, from building small satellites to building student rockets. And especially, so my passion is propulsion and very advanced propulsion. So to follow my dreams.
Mm-hmm. And I know this area is a little bit foreign to some people, even though it's starting to become more mainstream, especially when we think about these sci-fi technologies, like with the Star Trek warp drive that you mentioned. We have that public perception, and then the other one is with typical rockets that we've seen around since the 60s and so on. And it was very surprising to me to learn a little bit more about the other aspects of the field of propulsion that don't get talked about too much. So I thought we could quickly start off by laying a quick groundwork for what we'll be talking about. So I'm just going to make some quick statements as to what I understand. And please feel free to correct me if I say anything that's incorrect or if you'd like to add on. So to begin, when it comes to the propulsion industry as a whole, it is not just the typical rockets that we've seen in documentaries from the 60s and so on. We have that class of propulsion with chemical propellants, and it's mainly that class of propulsion that we see on TV when a rocket might be escaping Earth's atmosphere to get into space. But on top of that, we have a lot of other propulsion methods, from nuclear propulsion to electric propulsion to even micropropulsion. And when we look at these different propellant types, we also have to consider other factors such as whether the spacecraft is going from the Earth to escaping the atmosphere, or whether it's already in space, or whether it's making some kind of other maneuvers. And we have to consider factors like the size of the spacecraft, etc. And there are a lot of other factors and complexity here that most people don't typically see in the public, but I thought it was very interesting. And also, I thought it was interesting to hear about your specific work here. I know you focused a little bit on micropropulsion with a specific technology called field emission electric propulsion. Is that correct?
Correct, yes.
And it was very interesting for me to notice how, when it came to making these micro maneuvers in space, we never really think about that or see things like that, not in sci-fi and not in real life. So it was very interesting to see how much more of this field there is than with the images we see in sci-fi or in reality with just typical rockets. Do you think there's anything else to add when it comes to understanding the groundwork for what is out there when it comes to existing propulsion technology?
Well, I think you covered it all. So, of course, to go from ground into space, basically we do this with chemical propulsion. So that has been actually around not since the 1960s, but maybe something like for the past 1,000 years. Think about the Chinese and fireworks and whatever. So chemical propulsion is around for quite some time. Now, yeah, we can use it to go into space, let's say, since the technologies that were developed in Germany in World War II. So Werner von Braun, who then later came with his team to the United States, so they built then also the moon rocket. So they made chemical propulsion really big. And well, it's the big working horse so far. We bring things into space, and yeah, the big new innovation now is SpaceX and Elon Musk, who is making this a lot cheaper than it was done before. So by reusing technology is very essential. And also from manufacturing perspective, doing lots of things with 3D printing and, with lots of innovation, there's still a lot of innovation potential, even in classical propulsion technologies. So it's going to be much, much cheaper. So that's a good thing. And yeah, with chemical propulsion, you can reach orbit. So this is the first essential step. Now, once you're in orbit, then actually there are a couple of other options to choose from. You must not stick with chemical propulsion. So you named it, for example, electric propulsion. So in chemical propulsion, you are creating actually a hot gas, or a gas on high pressure. And this is exiting, in one direction, and you create thrust in the other direction. And the force that you generate depends on the mass flow rate and the exhaust velocity. So the higher the exhaust velocity, actually, the less propellant you need for the same amount of thrust, because force is mass flow rate times velocity. So if you go up in one factor, you can go down in the second factor. So that's propellant efficiency, so the higher the exhaust velocity. In chemical propulsion, there are some practical limits. For example, temperature. Well, you cannot go beyond a certain temperature, otherwise things are starting to melt. You can use active cooling and so on, but it becomes really, a big engineering project to do that. That's the one thing. The second thing is that the amount of pressure you can apply. Also here there are some engineering limits. When you go over them, then things become hugely expensive and big and complicated. So there's a limit in chemical propulsion with what you can do. And we are very close to the maximum efficiency right now from the propellants that we use. For example, we use hydrogen and oxygen, or we use methane and oxygen, something like this, that we burn. And what's coming out is more or less clean. So with hydrogen and oxygen, there's water vapor coming out. So that's a very clean engine. For example, we could do much better. If we would use, instead of oxygen, we would use fluorine or something like this, which is super toxic than what's coming out in the back. You would increase performance, but it's becoming very toxic. So that's not a very good idea. So you're limited in chemical propulsion with the propellants that we use and with the engineering complexity that we have. And with that, we can reach orbit. But now we have other options, like what I said, electric propulsion. Electric propulsion, instead of creating a hot gas, you are ionizing your propellant. So you're stripping off an electron. Now you have a positive propellant ion. When you apply an electric field, then you can accelerate this to much higher velocities that you could do using chemical propulsion with a hot gas. And that saves a lot of propellant. On the other hand, you need lots of power to use this engine. And it depends what kind of power option you have on your satellite or on your spacecraft. For example, if you think about, a big chemical rocket engine, if you have just rule of thumb, so for 1 cubic meter of combustion chamber, so the power that you're storing in the thermal power inside such a combustion chamber for 1 cubic meter is about a gigawatt, a gigawatt. That's the power output from a large nuclear power plant on Earth, That's what you have chemically, that you are burning on such a big rocket. So, of course, on your spacecraft, you don't have a gigawatt power supply. So let's say you get power from solar rays, then you get maybe some kilowatts or so. And with that, you can create very efficient thrust, but of course with much, much lower thrust values. You have these large rocket engines or whatever, you have maybe, you can have hundreds of kilonewtons, even meganewtons of thrust. With electric propulsion, you're much more efficient, but you're running maybe at a Newton or a sub-Newton, so 100 of millinewtons or so. but much more efficient. And when you're in space, depends if you have a satellite, you have some time. If you do, for example, a burn with chemical propulsion, then let's say this lasts for 10 seconds or something like this, yeah. And in chemical propulsion, let's say it lasts for months. So you can get the same impulse. So the impulse that you do to do a kind of maneuver change, in chemical propulsion, you have high thrust, and you can do this, you do bang, bang, yeah? So you start and you stop, yeah? And with that, you go into another direction. In electric propulsion, you have efficient thrust, but lower thrust value, no problem. You can do the same impulse. You turn on the engine, and then you wait for some weeks or months, and then you turn it off. And you can achieve the same thing, but it lasts longer. So you need a little bit more time. If you have this time, no problem, yeah. So then you can do things much more efficient, and satellites shrink in size because you need less propellant and so on and so forth. So once you're in space, then electric propulsion is very useful. So that's what you're going to do. Of course, it would be nice to have very high thrust, to do really high power stuff, plus to have very high efficiency. And that's the third thing that you mentioned. That would be nuclear propulsion. In nuclear propulsion, you're using a gas similar to chemical propulsion, but because you don't need to burn things, then you can stay, let's say, only with hydrogen. Hydrogen is the lightest gas around. So when you heat it up to a certain temperature, then your exhaust velocity and your efficiency is much higher than in chemical propulsion. You can use straight just hydrogen gas, so that's a great thing. You don't need to combust, you don't need to oxidize, you don't need an oxidizer for that. You just need a heating source, which is now a nuclear heating source. You're just heating up with a nuclear reactor, and off you go. So that's the ultimate kind of combination that you can do. And with that, of course, that would be the dream propulsion system once you're in space. With nuclear propulsion, with manned spacecraft, you can reach Mars in a couple of months. You can go to the Jupiter system in half a year or something like that. I'm always comparing this a little bit to, there are some famous poets, so let's say in Germany, maybe you've heard about Goethe, yes, so a very famous poet. So in these old days, so from Goethe, in these old days, you were using a horse carriage, okay? And he was going to Italy, and on his way back to Germany lasted half a year, because he also stopped at some villages and some cities, talked to some friends. And so his voyage from Italy back to Germany lasted, let's say, half a year. So that's the same time span if you have nuclear propulsion, that you can go manned to Jupiter, explore the icy moons or whatever, and check for alien life out there. So that's a technology, I'm sure, which is going to come, let's say, in the next decade. Yeah, so NASA is actively working on that. The Chinese are actively working on that. In Europe, there are some studies, paper studies, and that's going to come, so for sure. And that's the next evolution.
Mm-hmm. And when we talk about all of these different technologies, I know you highlighted a lot of the benefits and limitations of the different options. I think one of the key benefits that I've been thinking about, and you mentioned this with the evolution of technologies with SpaceX right now. Mm-hmm. One of the key benefits that is in the public perception is surrounded with costs and reusability, and being able to not only launch these one-off missions, such as going to, say, Jupiter, but thinking about what it takes to get to the next level of how humanity can become a spacefaring civilization. When it comes to these aspects like reusability, like sustainability and costs, could you talk about some of the benefits and downsides with the current generation of technology?
Well, reusability is a kind of a key factor, right, to bring costs down. Just think about, for example, when we bring something into space with expendable rockets, on the rocket that you ignite and you don't see it anymore. It's lost. So it brings some stuff into space and then it's gone. So let's say, rule of thumb, you have to pay, let's say, $10,000 per kilogram. Okay, a rule of thumb. Sometimes it's more expensive, sometimes a little bit less expensive. Now with this reusability approach from Elon Musk, you can bring this down, let's say, to, again, also kind of just rule of thumb, let's say to $1,000 per kilogram, okay? So he's bringing back this Falcon 9 rocket, or Falcon Heavy, They're bringing back the booster. Yeah, so this is a rocket. Unfortunately, you cannot go into space with chemical propulsion just in a single stage. Your payload fraction would be practically zero. So if you want to bring things into space, then when you go into space and you burn a lot of your propellant, then the rest of your tank, when it's half empty, it's useless mass that you're carrying with you. So you have to get rid of that. So that's why the rocket is done into stages. Yeah? So you're burning off the first stage. It doesn't reach this very high velocity that you need to get really into orbit. So it's coming back. This is the most easy thing to do. On the other hand, the booster, the first stage, is the largest part of your rocket. So from the cost point of view, that's great. If you bring back the biggest part of the rocket, if you bring it back, then that's great from the cost point of view. But still, you have the second stage, which is lost. Yeah? So the next generation that SpaceX is working on is Starship in Super Heavy. So Super Heavy is the first stage, and Starship is the second stage. And now the second stage is going to be fully reusable. So you have a whole system which is completely reusable. Plus, it's not made out of very expensive materials and manufacturing stuff like these composite materials and so on. But they use the stainless steel, which doesn't know. It looks shiny and great, yeah. Plus, it's super cheap. So if you get it done with stainless steel, then you get the cost down dramatically. You have full reusability, and then we're talking about bringing down the costs maybe to $20 per kilogram. And maybe if we do heavy reusability, it's aircraft like going into space, maybe it's $10 per kilogram. Now, that's in a price, where you can think of establishing a real outpost somewhere else, not just 4 people, trying to wait for the next crew to arrive, but then you can build a city on Mars. So this is the long-term view, which is 2 thumbs up. I mean, we were all waiting for that to happen. And if you watch Star Trek and you wonder, how can we make this a reality? Because this is really the next step for us humans. Yeah? So we came out of the water, we traveled the world, we built airplanes, and now we have to make a spaceship. So that's just really the next step.
Mm-hmm. And when I hear you talk about this, it's obvious to see your passion in this. And I'm sure with the experiences you've worked at with all the various space agencies in Europe and with NASA in the US, clearly it's not that people aren't passionate about this. Clearly it's not that there isn't a lot of research going into this. But when it comes to all of this progress being made, sometimes it's difficult to differentiate the new technologies being developed to the new applications that they're going into. So what I'd love to ask you is, when it comes to the current generation of technology that we have for propulsion, what are the common use cases that they're going into? But then what are the use cases that are still limited? We talked about one, which is setting up a space-based colony, but I'm sure there are others.
Okay. Let's put this, in very simple terms, okay? Everything is possible within our solar system. It just depends on will and money. So you can explore the whole solar system. We can establish an outpost on an icy moon, or Jupiter, whatever. It's just a matter of putting some money, and you have students, and you have your workforce, and you just go. There is no limitation, just money. Okay, money and time, and you can make it work. We can settle the whole solar system, but that's it. Okay, that's the limitation. So you can explore the solar system. You can fool around. You can do all crazy stuff. Yeah, we can mine asteroids. We can dig for alien life. In some icy moon world scenarios. We can establish a city on Mars and whatever. Yeah, but within the boundary of the solar system. That's the limitation. Okay, and it's a limitation because, well, if you want to crunch some numbers, yeah. So let's say you want to go to the next star, just the very next star. Okay, that's 4 light years away or something like that. Okay, just rule of thumb. You want to go 1 light year away, and you want to go there, let's say in 40 years. You don't want to come back. You just want to go there, let's say in 40 years, that you're still alive, that you can make a podcast, a live broadcast from Alpha Centauri and say, hello, I made it, so I've done that. So let's say 40 years or so. Huh? Okay, so you need a kind of a minimum size spacecraft. Let's say you take the space shuttle orbiter, okay? So that's the size of a spacecraft. It's not too roomy, but at least it is, we've built that already. And I crunched some numbers. It's large enough that in the cargo bay, you can put food cans for 40 years for 3 meals a day and some oxygen, so you can choose what kind of pasta you want to take with you, some chicken, some vegetables, whatever. For 40 years, you can have food cans, okay? For 40 years, no problem. It fits in the cargo bay and maybe some oxygen, whatever. Okay, so you want to go on a one-way trip in 40 years just to the next star. You have no clue if there is an interesting planet, if there is life out there, whatever. It's just the next star, okay? You have the space shuttle, you have your food and oxygen, and now the propulsion system, okay? Now let's take the best propulsion system, okay? The best propulsion system is nuclear propulsion, of course. And we said, sure, I mean, there are always temperature limits, okay? So even with your nuclear oven, you're heating up your propellant and you take just a simple hydrogen gas, but there's a temperature limit, otherwise your reactor is going to melt. Yeah? But you say, okay, well, then let's melt it, okay? Let's take the highest efficiency possible. So instead of using a nuclear reactor, you use a nuclear bomb, okay? So you just trigger EMC square, boom, yeah? I make the biggest explosion. I just take a small little nuclear bomb, I drop it behind my spacecraft, and I make and I push the button, okay? That's the biggest blast that you can think of, and you're lucky you're going in the desired direction. And so every couple of seconds you drop a bomb and you make boom. So actually that system has been studied in the 1960s. It's called Project Orion. And it's actually a great tool, I think, to get rid of nuclear weapons. We just use it to travel somewhere else, and these weapons are eliminated. So I think that's a great tool actually for that. So if you crunch some numbers, you have the highest efficiency propulsion system that you can think of. You have super high boost, you have the best efficiency, you use EMC squared directly, you have minimum spacecraft and so on. The amount of nuclear weapons that you have to carry to do that job is the mass of the sun, okay? So that tells you it's not going to be possible, okay? So you can explore the solar system, no problem, but you cannot go to the next star. So you have to invent a completely new type of propulsion system. That's option A. That's what I'm trying to work on. That's what I'm trying to do. Trying to think of how I can do propulsion different. It must be different because with conventional means, not a chance. Yeah. Or option B is we have to eliminate the time problem. Yeah. So that can be that maybe, yeah, we have to freeze the astronaut somehow, that he survives. We travel there, let's say it takes 10,000 years, then maybe that's more realistic. Or it's not us humans going there. Maybe it was our task to, create artificial intelligence. And let's say in 100 years, artificial intelligence is better than we are, or whatever. Maybe this was our task in evolution to help to create artificial intelligence. And the computer has maybe no time limitation. It has to repair some damage that it has from cosmic radiation. But if you have, some 3D printing on board or whatever, you print some new chips and whatever, maybe you can get rid of the time problem. And 40 years, for the universe, it's nothing. And 10,000 years is also nothing for the universe. So maybe it was our task to create something where this time problem doesn't exist. And then you can solve this problem as well. So you see, there are always solutions. You just have different things to choose from.
Mm-hmm. I think it's very interesting how you think about how to overcome the technical limitations here in terms of time, in terms of efficiency, in terms of speed. But these futuristic scenarios kind of bring me to my last few questions here, which were mainly around the areas of research that we're going to see in the future. Not just research, but also applications of this technology. So when it comes to the future of this area of research, what do you think are some of the most pressing areas that we have a gap of knowledge in, or a gap of technology or exploration in? And Do you think that the way to address these gaps are necessarily just more work on technology and exploring the possibilities and the different constraints that we have? Or do you think that there's also some untapped potential when it comes to the people side of things? Who's working on this? How many interdisciplinary ways are we considering this, etc.?
Well, I have a very special opinion about that. So, first of all, you cannot predict the future at all, okay? So I always wonder if when you make a proposal to propose something in research, what you want to do in the future, it's basically a lie. You cannot, you make a plan, yeah, but if you do real research, then you have no clue what's the outcome at the end of this research, if it's real research, okay? If I'm just saying, okay, well, I will try to, lower the costs of manufacturing this tool by using cheaper materials. Okay, well, this is probably predictable. But if you do, on a brackets, real research, so going into such kind of future areas, you have not a clue. Okay, no clue. Yeah. So just think back, 10 or 20 years or whatever. 20 years ago, did anyone predict that we would all have smartphones that are smarter than laptops, and got no clue? You don't know what's going to happen. Yeah. When Max Planck, so Max Planck was the founding father of quantum mechanics. Okay. So when he wanted to enter university, his parents were also curious about, if their son should study physics and whatever. And so they checked with other professors, and they went around and they asked around, if it's a good choice actually to study physics. Then the reply they got was, oh, we know everything in physics already, that there may be 3-4 areas with some unknowns, but he can already enroll in engineering, no problem. He doesn't need to study physics. And they said, okay, well, what are these 3-4 unknown areas? Okay. And then, one of them was something that he discovered, and now the next 100 years, are full of quantum physics. Now also, there's always the feeling that people think, that we more or less, we know already everything and we understand everything. There are just 2-3 unknown things, like what the hell is dark energy? The universe somehow behaves weird, but we cannot feel it, we cannot grasp it. We see some weird galaxy rotation curves, but has anyone seen it in the lab so far? You cannot predict what's going to happen if someone finds, what the hell is dark energy. The next 100 years of physics will be developed, okay? So the only honest answer is we just don't know. The future is unpredictable. That's a good thing. As a scientist, there's always things to discover, I'm sitting on my desk and I'm happy, okay, tomorrow I'm going to discover something new. That's great, okay? So you go to the lab, you do something totally unexpected, you use a measurement method that no one has ever tried, and you discover something totally unexpected. Superconductivity, okay? Till the 1980s, this phenomenon was around for, let's say, 70, 80 years or so. When I was studying physics and superconductivity, okay, I had a book, and in this book it was written in a preface, we will never ever find superconductivity, at temperatures well above 20 Kelvin. Then now we have superconductors with 100 Kelvin plus, okay? So it's very easy to say, oh, this is impossible. It's very easy to say so, but you just check history, okay? You just have to wait a little bit. So you have 2 options. If someone tells you something is impossible, either you can try option A, you try to prove him wrong, then you have to invest your time, your effort, and whatever. Or option B, you just sit and wait, okay? There are so many quotes where things have been proven to be impossible. So even when I say, again, you cannot go to the stars within our present knowledge, I just gave you some options. Oh, it's going to be possible, for sure. Let's say, I hope, of course, in my lifetime, but I'm an optimist. I can choose whatever I want to think. I can say, oh, that will be 1,000 years away. But that's not fun, I want to still be alive to see this stuff. So I say, hey, this will work within my lifetime, and I will try everything I can to make it work, But option B works the same way. You can sit back, okay, and if you can wait, let's say for 100 years, let's say for 1,000 years, okay, we will be all over the place, okay, in all these different stars or whatever, for sure. I can guarantee you. So option B works always. Just sit and wait. There's only our mind, it's just a limit of imagination. Jules Verne said, whatever you can imagine is possible because we are part of nature. How come we can think something impossible? So yeah, let's be optimistic, and the future is full of magic. So let's make some magic come true.
Well, I think that's a very great note to wrap up on. And I think it's just obvious, like in the past discussion, just to see your unique perspective and your, as you said, lifelong passion to make these scientific imaginations turn into a reality. So I really wanted to thank you for taking the time to talk about the state of this industry, the unique developments, but also the untapped potential that we really can't even begin to measure. And I think it's been a really insightful conversation on not just the specifics of the industry, but scientific progress and how to approach these kinds of very, very major questions in general.
Yeah, thanks. My pleasure.